Okay. طيب. Okay, again, is my voice clear?
Yes.
طيب, ممتاز. Let me go to the slides. طيب, بسم الله والحمد لله والصلاة والسلام على رسول الله وعلى آله وصحبه ومن والاه. I'd like to welcome you all to this lecture of ICS 253. Any questions before we proceed? No questions. Good. So everything seems fine. طيب, ممتاز. Okay. So basically, what we did last week was we looked at mathematical induction and strong induction. And now we will go over what is called the well-ordering property. The well-ordering property. طيب. Now, mathematical induction follows from the following fundamental axiom. In fact, I mentioned earlier that mathematical induction, strong induction, and the well-ordering property have the same power, right? So mathematical induction is actually based on the following axiom, which is called the well-ordering property. Now, what is the well-ordering property? Every non-empty set of non-negative integers has a least element. Every non-empty set of non-negative integers has a least element. Does that seem complex or simple?
Simple.
It's obvious.
It's obvious, huh? It's obvious. Right. Let's see how obvious is it. Let me change non-negative integers with integers. So can I say that every non-empty set of integers has a least element?
No.
No.
We can
No,
go
why
to
not?
minus infinity.
You can go to minus infinity. طيب, give me such a subset.
The integers themselves.
Smaller.
The negative integers themselves.
The negative integers, z minus, huh? Z minus. This is a non-empty subset. This is a non-empty subset of integers, yet it does not have a least element. It goes to infinity. Least element is not defined. Huh? So that shows the importance of the set being of a subset of non-negative integers, اللي هي natural numbers. Because we know that we cannot go to minus, we cannot, go to infinity if we go left when we have the set of natural numbers, صح? The set of natural numbers, the only direction that you go to infinity is what?
From the right.
Is from the right, right? Is from the right. Okay. طيب. Okay. So all of you agree that this is kind of a simple. This is kind of a simple concept, right? The concept that every non-empty subset of the set of natural numbers has a least element. Now, such simple concept will be used to prove the following situation, or to prove the following result. Okay, in a round robin tournament, every player plays every other player exactly once, and each match has a winner and a loser. So let me repeat that again. So basically, let's assume we have n players. Okay, assume that we have n players. Now, with n players, each player plays with all other players. Okay, so they will have a game, P1 with P2, P1 with P3, P1 with P4, until P1 with Pn, and then of course P2 with P3 and P2 with P4 all the way. So every pair have a match, and this match does not allow draws. So either so one of them has to win. Okay, so in each match we have a winner and a loser. Okay, in each match we have a winner and a loser. But let's continue. So we say that players P1, P2 up to PM form a cycle if P1 beats P2, P2 beats P3, P3 beats P4, blah, 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 PM minus 1 beats PM, and PM beats P1. Okay, so we will say that this is a cycle if each player basically in this sequence, beats the next one until the last one. Basically, the last one, PM beats P1. PM beats P1. Okay? Fine. So now, what we want to show is the following. Use the well-ordering principle to show that if there is a cycle of length M, where M is greater than or equal to 3, among the players in a round-robin tournament, the tournament that I just described, there must be a cycle of 3 players. There must be a cycle of 3 players. Okay? Fine. So basically, what do we want to show? Well, what we want to show is that if there is at least one cycle of length M, we have to have a cycle of length 3. Okay, of course, M is greater than or equal to 3. If we have a cycle of length M greater than or equal to 3, we have to have a cycle of length 3. This is what we want to show. Is that clear, ya shabab?
What does a cycle of 3 players mean? So P1 beats P2 and P2 beats P3 and P3 beats P1?
Exactly.
Thank you.
Okay, fine. So let's try to come up with the proof using the well-ordering principle, which is kind of a very simple statement or a simple result. Right. So let's assume. Okay. So assume that there exists a cycle P1, P2, PM. There exists a cycle P1, P2, PM where M is greater than or equal to 3. Okay. Assume that there exists a cycle P1, P2, PM where M is greater than or equal to 3. Fine. So this is what I'm going to say. I'm going to say consider all such cycles. ايش رايكم؟ Consider all such cycles. So what does that mean? Well, basically what I mean here is that I'm going to have a cycle of length, M1, M2, M3, and so on and so forth. If I know that there is at least one, then I know that there is, M1, M2, M3, even if it was all one only, even if it was all one. But basically, I can list them, right or wrong? All such cycles.
Yes, you can list them.
I can list all such cycles. Right? I have a cycle of length M1, I have a cycle of length M2, I have a cycle of length M3, I have a cycle. Fine. Who can tell me now? How can I use the well-ordering property in this case?
ممكن لأن ال 3 greater than يعني non-negative set.
So basically الM1 الM1 is what? Is greater than or equal to 3 صح؟
Yes.
والM2 is greater than or equal to 3. والM3 is greater than or equal to 3. Each and every one of these M's is greater than or equal to 3 صح؟
صح.
So isn't this a subset of the set of non-negative integers?
Yep.
Right?
It is a subset.
It is a subset of the طيب. What does the well-ordering principle say?
There is a smallest element.
There is the smallest element. Okay. So consider all such cycles, namely M1, M2. Well, let me write it in a nice way. Consider all such cycles with lengths, you know, M1, M2, M3, etc. Since the lengths form a subset of the non-negative integers, this set has a least element M prime. Okay, has a least element M prime with M prime is greater than or equal to 3. صح? It has a least element M prime with M prime greater than or equal to 3. طيب, what do I want to show? I want to show that there is a cycle of length 3, صح? Regardless of what is the value of M prime, right? Regardless of what is the value of M prime. Right. Now, if I prove to you that M prime is actually equal to 3, am I done or not done?
I think you are done, yes.
If I show that M prime is equal to 3, معناته خلاص. Right? If I show that M prime is equal to 3, then I have a cycle of length 3, right? So now what we will do is we will use an argument by contradiction. What does that mean? Let's assume that M prime is greater than 3, okay? And we will come up with contradiction. Right. Before doing that, do you realize that I cannot have a cycle of length 2?
Yes.
Why?
Because if P1 beats P2, then there's no way that P2 is going to be P1.
Because if P1 beats P2, there is no way that P2 beats P1, right? That's a contradiction. So I'm looking for cycles of length 3 or more, صح? I'm looking for cycles of length 3 or more. So if I can show that it can never happen, you know, that the least value is greater than 3, then I'm done. So this is what we will do. So for the sake of contradiction, assume that M prime is greater than or equal to 4, اللي هو least element. Okay, the M prime, which is the least element, is actually greater than or equal to 4. Right. Now, consider, well, let's do it on the other page because I want it, okay? Okay. Consider the cycle P1, P2, P3, P M prime. Because we said that M prime is the least, صح ولا لا؟ طيب let's look at the first 3 players in this cycle. Namely P1, P2, P3. ليش هيك هي كتبتها شكلها P3 أول واحدة؟ P1, P2, P3. Let's consider this cycle. Okay. Who can tell me what information do we know? The cycle. Who said that this is a cycle? This is not a cycle, صح? Consider the first 3 players in the cycle اللي هو ال P1 وال P2 P3 وعشان so that you do not confuse it that this is a cycle, I'm putting it in a set. The first 3 players. I need somebody to tell me what information do we know about the tournament regarding the P1 will P2 will P3 if I know that these are the first 3 players in the cycle P1 P2 P3 up to PM prime.
We know that P1 played with P2 and P3, and P2 played with P3 and P1, and P3 played.
Well, we know that regardless of the cycle, صح?
Yes.
لا, there is more information.
P1 beats P2 and P2 beats P3.
We know that P1 beats P2 and P2 beats P3, صح?
Yes.
Do we have any information about the game between P1 and P3?
No.
We don't have information. Do we have possibilities for the game between P1 and P3?
Yes.
Yes.
What are the possibilities?
Win or lose.
If there is no.
Exactly. So it's either P1 beats P3 or P3 beats P1, صح?
Yes.
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 Okay. So consider the following 2 cases for the match between P1 and P3. Right. Case 1. P3 beats P1. Who can now conclude the contradiction? This is the easy case.
If P3 beats P1, then that means we're done. That M is equal to 3.
M prime is equal to 3. So we basically found a cycle of length 3, صح? P1, P2, P3, P1.
Yes.
هاي يا شباب معاي ولا مع الأسف؟
Yes, it's equal to 3, the cycle.
The cycle is equal to 3. We have found a cycle that is equal to 3. So if P3 beats P1, this means that P1, P2, P3 is a cycle of length 3, which is strictly less than 4. Contradiction ولا مش contradiction?
Contradiction.
That's a contradiction. That's a contradiction. Right. So case 2 is the easy case. Now let's go to the harder case. Not that harder. Let's go to case 2. What is case 2? Well, case 2 is P1
P1 beats P3.
beats P3. P1 beats P3. So now if P1 beats P3, can anybody tell me if there is a contradiction?
No.
Okay,
Because
Yasser says no, and I say yes. There is a contradiction.
well, it's the cycle of length m.
It's still قصدك M prime يعني.
Yes.
Okay. Anybody can see or can come up with a contradiction, or in other words, can come up with a smaller cycle? I gave you a hint.
We just shift the positions of the players.
يلا قول لي ايش هو السايكل تبعك؟
I think it's since P2 beats P3 and P1 beats. Well, it depends if P2 beats P1 or not.
Do you care about P2, P1? Let me tell you, and I don't really care about P2, P1.
I think it's P3, P2, P1.
P3, P2, P1.
Yes.
But P3 did not beat P2.
Are we assuming that?
Of course. لأنه السايكل ايش بتقول؟ بتقول ال P1 beats P2 وال P2 beats P3 وال P3 beats P4 وال P4 beats P5. And then in the last player, PM prime beats P1. This is the assumption. In addition to that, now we are saying إنه ال P1 beats P3. Can anybody come up with a contradiction?
I think I figured this out.
يلا, go ahead.
Since P1 beats P3 and P3 beats P4, and then we all the way to PM. And then since PM beats P1, we have a cycle.
ايش هي السايكل؟
We repeat the steps like from P1 to PM.
لا بس قول لي السايكل، مش انا كتبت السايكل هذه كتبتها P1 P2 P3 up to PM prime. ايش السايكل اللي انت لقيتها هلا قبل شوي؟
It's not like a length of, it's not of length 4, but it's P1, P3 and P4.
ايوه now we're talking. See, if P1 beats P3, this means that P1, P3, P4, all the way up to PM prime is a cycle of length what?
Length M prime. Minus 1.
The cycle of length M prime minus 1. But what did I assume about M prime?
Greater
ordering
than
property.
Oh.
الويل ordering
Greater than
property
3.
ايش قال لي؟
Greater than or equal to 4.
No. Yeah. No. الويل ordering property ايش قالت لي؟ What did the well ordering property tell me?
Less than or equal to 3.
It is لا.
Greater than
Let's
3.
go. No. What did the well ordering property say? يلا هنورجيكم إياه. What did the well ordering property say?
Can it be a cycle if there is no P2?
What do you mean can't be a cycle if there is no P2? The P1 beats P3 صح؟ صح ولا مش صح؟
Yes, but where is B2? Why
I
did
don't
we?
care about P2.
But
care
B1 beats B2.
But I don't care. This is another cycle. P1 beats P3. صح ولا غلط؟
Yes.
P3 beats P4. صح ولا غلط؟
Yes.
I continue until Pm prime. Will Pm prime beats P1? So it's another cycle of length m minus m prime minus 1. Now, where is the contradiction? It's here. I wrote it.
There's an element less than m prime.
This set has a least element m prime. And I assumed that m prime was least. صح ولا لا? And no, this is the least such cycle. What did I do? I found a cycle of length what?
Minus 1.
Of length m prime minus 1, which is strictly less than m prime, اللي هي supposedly ايش? The least. And that is my contradiction. واضح يا شباب? So my contradiction in the first case is I immediately found a cycle of length 3, صح? I immediately found a cycle of length 3 contradiction. طيب. What was the contradiction in case 2? Well, I started with a cycle of m prime. I don't care what was that m prime. I know that m prime is greater than or equal to 4. But then I found a cycle of length m prime minus 1, which is contradiction because I assumed that m prime is the least. There is no such less than m prime. Okay, Shabab? So with this, basically, we end the proof, and using such a simple, such a simple idea, such a simple result, that any proper subset of non-empty proper subset of the natural numbers has a least value. Just using this simple thing, I was able to prove this result. Okay, I was able to prove this result, and with this we end up with section 2, and now we move on to section 3, recursive definitions and structural induction. So in this section, we will see that we may not apply, the induction just on formulas or rules that are closed form. No, we can actually also apply it on quote-unquote structures, okay, like functions, like sequences, like sets. Okay, so that's the idea behind this section. Okay, fine. Now, as an introduction, sometimes it is difficult to define an object explicitly. However, it may be easy to define this object in terms of itself, or basically recursively. And this process is basically called recursion. I need a show of hands. How many of you have heard of Quicksort?
Sorry, Doctor, can you repeat?
Sure. How many of you have heard of Quicksort?
Quicksort?
Yes. Okay. Can any one of you describe, those who raised their hands, can any one of you describe it? Describe a Quicksort. Kind of recursively. What's the idea behind Quicksort?
Isn't the idea behind Quicksort to divide the array into smaller arrays so that you can sort it quicker? And then
you can sort it. Well, that's
well, you do less comparisons.
Also, well, that applies also to merge sorts, huh?
That is true, yeah.
That applies to merge. But what was the idea behind the Quicksort? The idea behind Quicksort was you choose a pivot, you choose an element, right? You put it where it is supposed to be in the sorted array, huh? And then you put all elements that are less to the left, that are greater than or equal to the right, right? And then what do? Recursively sort the left and recursively sort the right. This is basically the recursive description of the Quicksort. This is the recursive description of the Quicksort. If you don't believe me that this description is actually much easier than the iterative version or than the iterative algorithm of the Quicksort, of course, outside the class, just go to Google and write, you know, iterative version of Quicksort. Look at the code and tell me if you understand anything from it. It's a total chaos, total mess. Why? Because you have to deal with all these, you know, indices. Okay, you have to deal with all these indices. But my point is that sometimes it is much easier to describe things recursively. It is much easier to describe things recursively. For example, if we look at this sequence, an equal 2 to the power n for n greater than or equal to 0, I can actually define it recursively as an equal 1 if n is equal to 0, or is 2 multiplied by an minus 1 if n is greater than or equal to 1. These two definitions are exactly for the same sequence. These two definitions are exactly for the same sequence. Similarly for functions, I can also define functions recursively. Quicksort, I can define algorithms recursively, right? Sets, we will see how we can define sets recursively, but maybe not today, but inshallah tomorrow. Okay. أول مرة هي بقول لكم tomorrow, مش day after tomorrow ولا next Sunday, صح؟ طيب. Okay. So let's just you know, have some Mickey Mouse examples. So find F2, F3, forget about F4 or F5. Let's just look at F2 and F3. If F is defined recursively by f of 0 equal minus 1, f of 1 is equal to 2, and up to, you know, n equal 1, 2. Of course, n should be equal to 2, 3, 4, etc., because 1 it has already been defined. 1 has already been defined. So starting from 2 to the end, let's assume that f of n plus 1 is equal to this. This is done in section 1. This was done in section 2. And let's do this one in section 4. Okay, the above one, part C. And this one is basically an exercise. Okay, so let's do this one. Let's try to find F2 and F3. Okay, right. So if F0 is equal to minus 1, F1 is equal to 2. Based on this definition of Fn plus 1, what is F of 2?
Three of n square, f1 square.
3 f of 1 whole square, أيوة.
Minus 4 f0 square.
Minus 4 f square of 0. Okay. In fact, it's better to put the exponent. It's better to put it at the top. Huh? Just put it there. So 3f square 1 minus 4f square 0. What is this equal to? 3 times f of 1 is 2, صح? 2 square minus 4 multiplied by ايش ال f of 0 square? Basically
minus 1 square.
Minus 1 square. ايش بيساوي هذا? So this is equal to 12 minus 4, which is equal to 8, صح? طيب, what is f of 3? Well, f of 3 is f of square of 2, صح? Minus, أيوة.
4f square of 1.
4f square of 1. So this is 3 times f of square of 2. We just found it is 8, huh? So 3 times 8 square minus 4 times, what is f of 1 whole square? اللي هي 4. مظبوط? And you can basically find it. You can have a calculator and computed. Right. So this is one thing. Another thing is, and this is very important, and hopefully, inshallah, you will see it in the upcoming assignment. What if I give you a closed form of a function and I ask you find the recursive definition? Okay, find a recursive definition. So for example, what is a recursive definition of the factorial function f of n equal n factorial? So if I want to write it recursively, how am I going to do that? Yalla. Nawaf, go ahead.
It's first we put the base case, which is when n is 0, it's equal to 1.
N equals 0. So in this case, n factorial is equal to 1. طيب والسكند كيس ايش مالها الان؟
ويت انا نواف ولا كان في واحد ثاني رافع يده؟
هو كان نواف رافع يده، بس الظاهر كان رافع يده من زمان. انت ريان صح؟
معذرة دكتور، معذرة كنت رافعها من يوم ما سكنت.
اوكي طيب اوكي يلا جو اهيد كونتينيو.
طيب إذا ما هي 0 بتكون n times n minus 1 factorial.
n times n minus 1 factorial اللي هي n times
يعني
f of n minus 1 صح؟
f n minus 1. Yes.
n times f of n minus 1 وال n is greater than or equal to ايش؟
1.
وال n is greater than or equal to 1. وال n is greater than or equal to 1. طيب who is going to give me a recursive definition of this summation? Sigma ak from k equals 0 up to n. Again, notice that, you know, recursive definitions always start with a base case and then kind of the recursive step or the inductive step, which will lead, if you do the expansion, it will reach the base case. So يلا ايش البيس كيس هنا؟
k equal n.
لا. ايش البيس كيس؟
k equals 0.
a of 0.
k is n plus 1.
مين اللي equal 0؟ الكي ولا الان؟
n equals 0.
الكي.
n equal 0.
How the n is equal to 0 دكتور؟
الn is equal to 0 صح؟ الn is equal to 0. So
it will start from 0.
Exactly. So if n is equal to 0, what am I going to write here?
0.
A0.
A0 ممتاز. A0. So sigma ak from k equals 0 to n is equal to A0 if n is equal to 0. طيب. If n is greater than or equal to 1, what shall I put here?
an plus the summation and then n minus 1.
An plus the summation of ak from k equals 0 to n minus 1. From k equals 0 to n minus 1. Okay? Right. So this is how we, define functions that are in closed form. We can basically define them recursively. Right. So now we will see the first form of, or one way of proving a result, and I will ask you now how. Fibonacci numbers are defined recursively. So how they are defined, f0, f1, f2, f3, they are defined by f0 equals 0, f1 equal 1, and then fn equal fn minus 1 plus fn minus 2. Fn equal fn minus 1 plus fn minus 2 for n equal 2, 3, 4, etc. Right. What is the result that I want to show? Show that whenever n is greater than or equal to 3, that fn is greater than alpha to the power n minus 2, where alpha is 1 plus square root of 5 divided by 2. Okay, this is what I want to show. Anybody has any idea of how can I show this?
Write the recursive definition first.
Write the recursive. So which proof technique you are going to use?
Induction.
Write the function.
Induction. Mathematical ولا strong?
Strong, because you have
because I have fn-1 or fn-2, صح?
Yes.
I need to apply the induction twice, right? So basically proof, oops, ارجع للخط احمر. Proof by strong induction. طيب, let's start with the basis. Now, for now, let's do one basis, and then we will see whether we are going to need another one or no. What is the basis in this case?
Zero and 1.
Look at the result. Don't look at the definition of the Fibonacci sequence.
If n is equal to 3.
If n is equal to 3, صح? If n is equal to 3. So I need to find f3. I have f0, f1. I don't have f3, right? So what is f3? Well, let's see. What is f2?
F0 plus f1, which is 1.
It is f1 plus f0, which is equal to 1. So therefore, what is f3? It is
2.
f2 plus
f2
f1
plus f1,
which is equal to 2, صح? Which is equal. So for the basis, I'm gonna do it for P3. So is it true that f3, which is equal to 2, is greater than 1 plus square root of 5 divided by 2 to the power 3 minus 2 is equal to 1 to the power 1, which is basically 1 plus square root of 5 divided by 2. Do you see that this is true, ya shabab? When is this equal to 2 actually? If I had under the square root, which number?
4. Oh no. 9.
9 صح؟ فdefinitely
Yes.
Definitely 2 is greater than this number, صح? Definitely
Yes,
2 is
it
greater
is.
than this number. طيب. So let's go to the inductive step, and then we will see if we need any other basis. We will do it from the proof. So let's go to the inductive step. So assume that the result holds. Is our own Nashiba for all k. مالها k? K less than or equal to n, greater than or equal to, for now, let's say 3. Okay, k less than or equal to n, k less than or equal to n, greater than or equal to 3. To show that the result holds for k equal كم? For k equal n plus 1, صح? i.e., what do I want to show?
Yes.
i.e., what do I want to show? That f n plus 1 ماله?
Greater than 3, greater than equal.
Greater than, ما في equal. It's greater than alpha
Alpha
3.
to the power. Which power?
n minus 1.
-2.
minus 1. ترى عوضت هنا ب n plus 1 صح؟ ف if I put here n plus 1, this becomes ايش؟ n plus 1 minus 2.
-2, so it becomes n minus 1. Yes.
So it becomes n minus 1. Okay, so this is what I want to show. طيب. Okay, so how can I use an induction hypothesis? Well, since fn plus 1 is equal to fn plus fn minus 1, this is the definition of the Fibonacci, صح? fn plus 1 is equal to what? fn plus fn minus 1. We can use the induction hypothesis. The induction hypothesis on fn and fn minus 1 if n was greater than or equal to 3 and n minus 1 was greater than or equal to 3. صح؟ مش هذا هو؟ For all k greater than or equal to 3, less than or equal to n. طيب n, is it greater than or equal to 3?
Yes.
Yes, n is greater than or equal to 3. طيب n minus 1? According to this, is it greater than or equal to 3?
No.
No.
No. So what does that mean? This means I need n to be
The
greater
base
than or
should
equal.
be start.
I need, in
4.
addition to the 3, I also need the 4. So that I can go back minus 2. Okay, so that I can go back minus 2, I need n equal 4. I need n equal 4. So that's why I will come here. I will come here and I will, erase this 3 here. And I will say that this is equal to 4. صح? K should be greater than or equal to 4. And I need P of 4. Now, the question is, what is P of 4? Well, P of 4 is basically F4, صح? Now, what is F4? F4 is F3 plus F2.
F3 plus F2. 2 plus 1.
Which is 2 plus 1, which is equal to 3. Now, is this greater than in 1 plus square root of 5 divided by 2 all square? The answer is yes. You can check it. Okay, either you use a calculator, how you basically square it, and it will be very obvious that it is greater. That 3 is greater. We don't have time to do it here, right? So let us now worry about the inductive step, right? So now I can use induction on fn who fn minus 1. Okay, since n now is greater than, or k is greater than or equal to 4, less than or equal to n, now I can use it. So therefore, fn plus 1, which is equal to fn plus fn minus 1, using an induction hypothesis, this value here is greater than what? fn is greater than ايش? alpha to the n minus 2, صح?
Yes.
fn minus 1 is greater than ايش? alpha
n minus 1.
n minus 1 ولا n minus 3?
Minus 3, yes.
n minus 3, صح? fn alpha to the n minus 2. Okay, that's the induction hypothesis. So fn plus 1 is greater than alpha to the n minus 2 plus alpha to the n minus 3. What is this? Well, which one is smaller? Let's try to take a common factor. n minus 2 or n minus 3 smaller?
Minus 3.
n minus 3, right?
3.
So let's say alpha to the power n minus 3. And now what do we have? We have alpha to the n minus 2 divided by alpha to the n minus 3. This is alpha plus 1, صح? Until now, we haven't reached anywhere. However, we are finished. We are done. You know why? This is a property of alpha itself. احنا ايش قلنا الالفا؟ 1 plus square root of 5 divided by 2, صح?
Yes.
Let's try to find an equation. What type of equation do we have here? Let's شو رايكم نجيب ال 2 to the other side. ايش راح تصير؟ this is equivalent to 2 alpha equal 1 plus square root of 5 صح؟ which is equivalent to let's bring the 1 to the other side. 2 alpha minus 1 is equal square root of 5 صح؟ طيب شو نسوي هلا؟ square both sides. 4 alpha square minus 4 alpha plus 1 is equal to ايش؟ is equal to 5 صح؟ طيب مش this is equivalent 4 alpha square minus 4 alpha minus 4 equal 0. ايش سويت هنا؟ جبت الخمسة ووديتها للطرف الثاني صح؟ طيب can I divide by 4؟ الألفا سكوير إيش بتساوي؟ alpha square is equal to alpha plus 1. In fact, I don't know if anybody knows, but do you know that this is called the golden ratio?
Yes.
This is the golden ratio because it's the solution. It's one of the solutions to the equation x square minus x minus 1 equals 0. فالألفا سكوير إيش بتساوي؟ هي نفس الألفا plus 1. So basically, this is equal to what? This is equal to alpha to the power n minus 3 multiplied by alpha plus 1. ايش هي الالفا plus 1? Alpha plus 1 is exactly the same as alpha square, which is equal to alpha to the power n minus 1. Right. Isn't this what we want to show?
Yes.
Fn plus 1 is greater than alpha to the n minus 1. Fn plus 1 is greater than alpha to the n minus 1. واضح يا شباب؟ معلش أخرناكم شوي 5 minutes بس also we started a little bit late because of that problem. Any questions?
Doctor?
نعم.
Something weird I haven't seen mentioned is that induction can only be used when you already know your answer. You just want to verify it.
Well, you already know it. Maybe you have
conjecture.
Yeah, maybe you have it as a conjecture, and then you use an induction to prove it. يعني by trial and error, you find the formula. You find the formula by trial and error, and then you try to prove it using induction.
Okay, I see.
Okay. Any other question يا شباب? طيب, sorry for keeping you late, but at least يعني we are online. We're not. I already have seen people running around, to maybe catch their next class or next lab. طيب, thank you very much for attending, and inshallah we'll see you tomorrow. Offline مش online, huh? Face to face.
Thank you دكتور. التمارة هذه feels weird.
كيف؟
التمارة هذه feels weird. أول مرة
بنستخدم tomorrow صح؟
أيوه.
العادة day after tomorrow أو next Thursday أو next Sunday، بس هالمرة لا tomorrow بنشوفكم إن شاء الله. يلا الله بعين. نراكم على خير إن شاء الله. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.